In this video, we're going to talk about equivalent force systems, principle of transmissibility, and force and couple systems. The section is 4.7 on your Hibbeler's book, and it's called Simplification of a Force and Couple System. So let me ask you this. Let's say you have a body, just like this one here, and you have several forces acting 750, 500, and then these two guys over here. And I ask you, so what do you think is going to be the end effect of all these forces at this point O? So asking the question, what do you think happens at point O, is the same thing as asking you to calculate an equivalent force system, equivalent system. That is, we want to reduce all these forces, in this case 1, 2, 3, 4, maybe have 6, 7, 10, 20. We want to reduce it into a single force and possibly a moment here that is going to capture both the tendency to try to translate this body or the tendency to try to rotate this body. So to be able to calculate this, first we need to review the principle of transmissibility and force and couple systems. Now let's say you have any body, right? Not just this one, any body, this arbitrary shaped body, and you have, in this case, just one force being applied to it right at this point. Now the question is still the same. So let's say what happens if we have a force applied at this point, but then again, we're interested at this point O, so another point. So to calculate what's going to happen at this point O, we're going to do a very quick mathematical trick. And so look at this. So we have a force F over here. What I'm going to do is go ahead and apply here at this point O, which is the point that I'm interested in. I'm going to apply a force F over here of same magnitude and direction as the original one. But I'm also going to apply one that has the same magnitude at the opposite direction. Okay? So what this allows us to do is to be able to kind of transmit what's going on over here at this point O. Now, when I added these two forces of the same magnitude but opposite direction, essentially I didn't add anything. Because let's say this force was 100, I added 100 going that way, 100 going to your left over here. Essentially, these two forces cancel each other out. But instead, what we'll do is, these two will cancel out because they're the same magnitude, opposite direction, but these two also cancel out because they're the same magnitude in opposite direction, right? So by adding these two over here, I essentially can cancel this guy over here, right? Which is going to cancel to this one over here. Now look at what happened. I had an original force over here. I added here an equal and opposite pair at point O. Those two that were previously here cancel. Now I'm left with this one. Essentially what happened is that I slide that vector, right? So this is the same thing we've been talking about in class, that we can slide any vector along its line of action. And this is going to hold true again. Along its line of action, I can, anytime you see a vector, like for example this one, I can slide it up and down, and it's not going to change the effects on the body. This one over here that's at an angle, as long as I slide it along its line of action, it's not going to change again. That is called principle of transmissibility. You can think of it as just, we can treat any vector as a sliding vector. So again, if you're interested to find out what's going on a point that's on the line of action of the force, you can simply just slide that force to that point, no problemo. So what happens when the point of interest is not on the line of action of the force? Well, we can do the same mathematical trick. We'll add here two linear forces with the same magnitude as the original force. Again, these two are going to cancel each other out. So I haven't added like a new force, right? Again, because they cancel each other out. But we can change the way we look at these, right? Because now look at this. I have two parallel forces of same magnitude, opposite directions, that they're separated by some distance d over here, right? So what that means is we have a couple. So the moral of the story is, if I want to move a force that is acting on a body to a point that is not in its line of action, I can do so, but I must also capture this couple moment over here. So another way to think about it, a very quick one, is say you have your arbitrary body, you have this force acting on it, and we want to figure out what's going on at point O, right? Very quickly, just slide that vector over here, but realize it's like we're pinning this body here. So not only do we have the force translating, but also we have something that wants to rotate it, right? Rotate it like by this distance over here. So we're going to calculate that couple. So now let's go back to this original problem where we have a body and several forces acting on, and what we want to figure out is we want to replace the force system by an equivalent force and couple moment acting at point O. So now you know that if I want to essentially like think about moving these forces or capturing the same effect at this point O, right, we're going to do so with a force and a couple moment. Now figuring out the force is very simple. This is just the resultant. So we're going to sum all the forces together to calculate that resultant. Hence this formula over here. To figure out the resultant moment at point O, well, it's going to be a function of two things, right? One, we can have the scenario where a force does not pass through point O. So for example, over here, the 750 force does not pass through point O. It's going to generate a moment about point O, right? So these are these terms in this formula over here. The resultant moment about point O is the sum of the moments from all the forces about point O plus any existing couple moment. So in this example, look at what we have. 750 doesn't pass through point O. It's going to generate a moment about point O. The 500 force probably doesn't pass through point O, so it's going to generate some moments. And then over here, right, we have two forces that are parallel, same magnitude, opposite direction, separate some distance. This is a couple, right? So this couple over here, we're going to have to account for this. So let's go ahead and start. Now to be able to calculate the resultant force, we just have to sum the forces, right? This is a 2D problem, so we're going to have to sum forces in the x and the y direction, right? So we have a vertical force, something here at an angle. Oops, and I forgot here the direction. This is 3, 4, 5. And then these two horizontal forces, right? So let me go ahead and change this force that it's at an angle. We'll calculate its x and y components. So along the x-axis, right, this is going to be 500 times 3 divided by 5, and in the y direction, it's 500 times 4 divided by 5. Okay, once we do that, it's like we delete this guy, right? We don't need it anymore. Now we have its x and y components, and let's go ahead and calculate what these values are. So 500 divided by 5, that's 100 times 3, that's 300 newtons. And then 500 divided by 5 times 4, that is 400 newtons. So now we can go ahead and start summing the forces in the x direction. So sum of the forces in the x direction. Again, I'm going to sum forces. I'm going to sweep from point O to the right. This is vertical, vertical, horizontal. It's 300. Notice it's pointing in the positive x direction, right? Because we always say, hey, if it points in that direction, it's a positive. So this is a 300. And then we have some horizontal here, minus 200 plus 200. Essentially, these two cancels out, and the sum of the forces in the x is just 300 newtons to the right. Now let's go ahead and do the sum of the forces in the y direction. Again, anything that points up is positive. I'm going to sweep from left to right. I started with 750. It's pointing down, so that's a minus 750. Then we have 400 pointing up, so plus 400 newtons, right? This is horizontal, horizontal, and horizontal. These guys are not going to show up. So what we have is minus 750 plus 300. This is going to give minus 350 newtons, right? So we can put a minus in the y, or even better, let's put a down arrow over here. So now we have the x and y components. What we want is the resultant, right? So to be able to calculate that resultant, we just have to take the square root of 300 squared plus 350 squared. So we do that real quickly. Square root of 300 squared plus 350 squared. Square root of that gives me that this guy is 460.97. So I'm going to ahead and round it to 461 newtons. Again, that is the magnitude. 461 is the magnitude. We need the direction, right? So we have a magnitude, 461. What we need is the direction. So remember how to do that? we plot our x and y axis here. And actually go ahead and plot or draw these two components. So 300 to the right, 1, 2, 3, roughly somewhere here, 300. We have 350 going down, so 1, 2, 3 and a half. This is the y component, and so where the two lines meet, that's our resultant. If we want to figure out this angle theta, given with the x-axis, right? We can do so by using SOHCAHTOA, by taking the inverse tangent. So theta equals inverse tangent of my opposite. So what's my opposite? 350, and my adjacent leg, which is 300. So inverse tangent of 350 by 300 gives me 49.4. So theta equals 49.4 degrees. Now remember, usually we take our angles this direction as positive. So we went the opposite direction, we can say this is minus 49.4 degrees. So this theta is 49.4 degrees. Next, what we need to calculate is the resultant moment, right? At the end of the day, these forces might want to also twist this body or create a tendency to rotate this body about 0.0, and that's what we're going to capture next. So remember our formula, right? The resultant moment about 0.0 is going to be the sum of the moments of any force that does not cross through 0.0. It can create a tendency to rotate, plus any existing couples. Okay, so I'm going to sweep from left to right over here. I'm going to calculate what are going to be the individual moments, right, of each of the forces about 0.0. So first we start with this one. We have 750, right? It's vertical. It does not pass through 0.0, so it can create a tendency to rotate, right? So remember, just the original formula for the moment is the force times the distance. So the force is 750. The distance for the moment arm from that force to 0.0 is 1.25. So 1.25. We have force, distance, and next is the sign. Is this going to create a positive moment or a negative moment? So again, remember, our convention is if it's counterclockwise, it's positive, right? Here's the 750 is going to spin it clockwise, so that's a negative moment. So as we continue to sweep here to the right, I'm going to now take into account this vertical force, which is 400 newtons. The distance, perpendicular distance between that force and our 0.0 is now 1.25 plus 1.25 or 2.5. And then what is the direction, right? This force now points up. I'm at 0.0, right? So this is going to make it spin counterclockwise. So that's a positive moment. Notice here we also have the horizontal component. There's this 300 Newton force that does not pass through 0.0, so it can create a moment. So the force is 300. The distance, perpendicular distance to 0.0 is 1 meter. So 300 times 1. Sorry about the colors. Right? Now what is the direction? Again, here we can apply that principle of transmissibility, right? And it's like this 300 and force is pointing that direction. So if I'm at 0.0, 300 points that way, it's going to make it spin clockwise, which is a negative moment. Right? So we're done with 1, 2, 3. Now we have these two other forces. Now there's two ways to go about it. We could try to figure out what is the distance between that force and 0.0, or better yet, we can realize that, hey, I have two forces that are same magnitude, opposite direction. right? They're separated by some distance here. They're going to create a couple. So we can think of these guys as just a couple moment over here, right? And the formula for a couple moment is just force times distance, so 200 times 1. Let me make it blue for this couple. So it's 200 times 1. And what is the direction of this couple? This guy's going to spin this direction, right? That's a counterclockwise direction, which is a positive one, right? So this here is from our couple. All of these over here are from the moments caused by the forces that are not passing through point O. So all we have to do now is type that into the calculator, and let's see what we get. So minus 750 times 1.25 plus 400 times 2.5 minus 300 plus 200. So if I plugged it in correctly, this is telling me that the resultant moment about 0.0 is minus 37 and a half. Again, minus 37 means, right, that is going to be a clockwise moment. So now we figure out this resultant moment is 37.5. Remember the units here, we have newtons and meters, so 37.5 Newton meter, and it was a negative moment, so it was clockwise, CW. So there we have it. We calculated the resultant force, 461 at minus 49.4 degrees, and a couple moment acting on 0.0, the 37.5. This is what we call an equivalent system. So what we're saying is this force and this moment have the same external effects as all of these forces combined. When is this stuff useful? Let's say, for example, this is where we want to fix or support this pipe assembly, and we want to figure out, okay, what is the force is going to be at this support? Well, now we have the force in the couple. That's one way to think about this, and you'll see other applications of this kinds of operations once you get to solids and machine elements courses. So just to recap, right, we can slide any force along its line of action, no problem. Principle of transmissibility, we can treat them as sliding vectors. If we want to figure out what is the effect that that force at a point that is not on its line of action, like in this example of this 0.0, we're going to have to capture not only the force that's trying to push this thing down at 750 over here, but also a tendency to rotate over here. So as you do in class, I'm going to ask you if you found any mistakes on my calculations. Please do let me know by leaving a comment down below. I'm also going to link you some videos over here, other examples where we do simplification of force and couple systems from myself as well as from other very good sources. So if you like the video, please give me a like.